All right. Today, we're diving deep into the quantum world. We're going to uncover this really beautiful kind of hidden secret about how particles can actually remember their own journeys. It's a memory that's not stored in time, but in the geometry of the path itself. I mean, think about that for a second. It sounds like a riddle, doesn't it? Imagine you go on a long trip. You end up exactly where you started, in the same physical spot, but something about you is just different. The path you took has left some kind of permanent, invisible mark on you.
Well, this isn't just some philosophical puzzle or a thought experiment. For quantum particles, this journey's memory is a real, measurable thing that happens all the time.
So picture a particle, right? It starts out in a certain state, it goes on some kind of journey, and then it comes back to that exact same state. You'd think nothing has changed. And yet, internally, something is fundamentally different. So the question is, how on earth is that even possible?
Okay, to solve this mystery, we need to look for a hidden clue, a property of the particle that isn't immediately obvious when you just, look at it. And this clue, this is what physicists call the particle's phase.
So what is this phase thing? Well, you can think of it like a particle's own internal clock, or maybe like a tiny compass needle that it carries around. It's this hidden property that describes its cyclical nature, but it's not something we can see directly. It's really part of its secret quantum identity.
For a long, long time, the thinking here was pretty straightforward. The longer a particle's journey took, or the more energy it had, the more its little internal clock, its phase, would tick forward. Simple, right? It was all about how long and how much energy. But as it turns out, that wasn't the whole story. Not even close.
To really get what's going on, let's use a visual analogy. It makes it so much easier to understand. Let's just imagine we're moving an arrow across the surface of a giant sphere, kind of like our planet Earth.
Okay, picture this in your head. We start at the equator, and our arrow is pointing straight north. Now we just slide it, we don't turn it, we just slide it up to the North Pole, keeping it aligned with its path. Then, from the pole, we slide it back down to the equator, but along a totally different line of longitude. Now look what's happened. The arrow is back at the same latitude it started from, but it's no longer pointing north. It's actually rotated.
And this is the real kicker. We never actively twisted that arrow, not once. The change in its direction, that rotation, came purely from the curved path it traveled. The geometry of the journey itself is what forced the arrow to twist. The bigger the area enclosed by the path on that sphere, the bigger the twist. So this simple, really elegant analogy of an arrow on a sphere, well, that's the key. That's the key to understanding a really profound discovery in quantum mechanics, made by a physicist named Sir Michael Berry. Back in 1984, in this landmark paper, Berry showed that a quantum system's internal phase can behave exactly like that arrow we just imagined. As the system's environment changes and then returns to where it started, the system's internal phase gets twisted, and the amount of that twist depends only on the geometric path it took. So this gives us two totally different ways a particle's phase can change. The old way, the dynamic phase, that's like a runner's stopwatch. It only cares about how long you've been running. But Berry's incredible discovery, the geometric phase, that's more like a map of your journey. It doesn't care about the time at all. It only cares about the shape of the path you took through the mountains.
And that, in a nutshell, is the Berry phase. It's a fundamental piece of quantum mechanics that was, believe it or not, kind of hiding in plain sight for decades. A memory of geometry, imprinted on a particle's deepest, most fundamental properties. Okay, so this might all sound a little abstract, right? A particle's secret memory, a twisty path, but the discovery of this geometric phase has completely changed how we understand and even how we manipulate the quantum world. So why does this actually matter in the real world?
Oh, it matters a lot. The Berry phase is absolutely crucial. In quantum computing, you can use these geometric twists to create what are called topological qubits. They're naturally resistant to errors, which is a massive hurdle in building powerful quantum computers. It's also essential for understanding advanced materials like graphene. The Berry phase is literally what explains its unique ability to conduct electricity so well. Its principles even pop up in optics and fluid dynamics. It's truly a cornerstone of modern physics.
So, the discovery of the Berry phase really shows us something profound, that sometimes the most important truths aren't about the destination or how long it takes to get there, but about the shape of the journey itself. And it really makes you wonder, what other fundamental secrets are just woven into the very fabric, the very geometry of our reality?